this is my 8-bit register. The leftmost button is the clock signal coming in from the monostable 555 timer IC. The rightmost button is the data button, and the middle button is the reset. This project showcases the concept of serial data transfer, where one bit of data is input on each rising edge of the clock pulse and is shifted from one D flip-flop to the next, allowing for a continuous stream of data to be loaded into the register, simulating how a computer memory is stored. So let's look at two latching emulations to understand the concept and uses of latching and feedback first. So when the button connected to voltage here is pressed, the LED turns on. So basically the high goes into the NOT gate, outputting a low, and then that low goes to the next NOT gate, outputting a high, turning the LED on, and that high also goes into the input of the first NOT gate. So when the button is released, the output will always be, in essence, high. Now, if I were to press the other button that's connected to ground, the low essentially becomes a high, that high becomes a low, the LED is off, and then that low is connected to the input of the first NOT gate. So even after the button is released, so when the button is released, the output will still be low. So now we're going to look at the circuit up top here. So in essence, the idea of feedback can also be used as like a buffer to strengthen the signal. And the buffer mechanism can be visualized in this case with the slide switch with the input in the middle pin. The other pins are connected to the voltage, and the other the right is connected to voltage and the left is left floating. So when connected to power, it will send a 1 to the NOT gate, outputting a low. That one enters another NOT gate, outputting a high, which is connected to the LED, which allows it to turn on. So now, if the switch is toggled to the other side, the input connecting the switch will be floating. However, if I were to do that, because of the feedback from before, the input of the first NOT gate is a 1, which in short allows the LED to stay on. The LED will be a bit dimmer as the voltage the LED gets is slightly lower than VCC. So now that we understand how latches work and the idea of feedback, this is the inside of a D flip-flop, and we can see the feedback aspect in there along with the latch aspect. So flip-flops and latches are similar, except that flip-flops are edge trigger devices, meaning they change their state at the rising or falling edge of a clock signal, in this case, rising edge. Latches are level sensitive devices, which means they continuously respond to changes in input data as long as the enable E input is active. This is a 4-bit version of the circuit, but the 8-bit and 4-bit work the same way. It's just that there are more bits to go through. Initially, clock and D are both low, thus Q bar is high, and Q is low. When D is high, Q is still low. When clock is high, Q is still low. However, when both are high, the Q becomes high and Q bar becomes low. Now, despite the two inputs in the next flip-flops being high, Q is low because they only change their outputs at the rising edge of the clock signal, of course with their D input being on the entire time. Because the 555 is configured in monostable mode, the only time it will change its state to high again is if the clock input is pressed again. So the flip-flops after the first one are still latched to Q bar. It doesn't matter if both inputs are high. There has to be a rising edge in the clock signal while their D input is high. The D inputs were high only after the rising edge of the clock signal, even though the time difference is very minute, which shows the great precision of these chips. So as the clock button is released, the first D flip-flop latches onto the high in Q, while the rest still latch on to their high in Q bar. Now if clock is pressed again, the first flip-flop stays high, and now the second flip-flop's Q output will be high, with the rest of the Qs after the second flip-flop still being low. This process repeats for as many bits as you have. So there's also a shift operation in the register, where binary values can be moved from one flip-flop output to the next, triggered by the clock pulse without changing the existing data, which will always just be in a low state. So this operation effectively repositions bits within the register, allowing us to shift them to the left or right. For us, moving to the right would be similar to multiply the binary number by a power of 2. So let's say that Q is high for the first bit. So as we can see, that's high. Now having D low, I'll continually press clock, allowing the LED to cascade to the next Q outputs until the end. And this is actually simulating what would happen if our circuit was configured in astable mode rather than monostable. So we're simulating the continuous oscillation manually. Now, combining the idea of the shift operation with the circuit in astable mode, if we were to have, let's say, this as our output first, in astable mode, the circuit would have just automatically shifted these operations until the output is null.
Thank you for watching.